Today, what we're going to look at is doing a little bit more of a quantitative analysis of changes in the snow depth from place to place versus from year to year. Okay, so we looked at the map distribution. We saw how much the total depth is changing from location to location, and we looked also at changes from year to year when we looked at the overall distribution. So now we're going to try to do the same thing, but in a more quantitative way. We're trying to answer the question: what is more important for the time of the snow? Is it changes from year to year, or is it changes from place to place? So we know that coefficient 2 corresponds to whether the snow season is late or early. And now we want to see this dependence. And what we're going to use squared error or root mean square error to quantify the strength of the dependencies. So we're going to use it as basically as a yardstick to decide which one of these two influences is more important. So we start as usual by reading data into a data frame, and here I'm just filtering the data according to a particular station and looking at it, so you have all of the parameters that you've seen before. And then I'm selecting from that just the station, the year, and the second coefficient. Okay, so that's the data that interests me, and here I put it into a pandas format, and so that will make it easier for me to plot. So in order to analyze the interrelationship between the two, one of the convenient things would be to have a new table where the columns are the stations and the rows are the years. And we do that with the command called pivot. So pivot is a useful command that takes long lists of combinations and makes them into a table where you have some columns. Here it's the station, and you have a rows. There are the years, and the values are coefficient 2. Okay, so now we have that big table. And this table goes over all of the stations in New York State, and it goes from the year 1892 to 2013. So apparently we have a huge amount of data, but if you look here in the first years, 1892, you see that almost all of the stations actually were not defined. Probably they weren't even there. So how many of the stations are NaN, or station years combinations are NaN? So we have 328 stations, and we have 121 years, but about 80% of those are NaN, okay? And it is, in general, not a good idea to do statistics when you have very sparse data. So we would like to try and make the data a little bit less sparse. Okay, so one way to look at the data is at the distribution of the number of stations that have a particular fraction of the years undefined. Okay, so there's a lot of stations that have 120 years undefined. So that's basically, we have 121 years, so you can't have more than that. And then there are stations that have less undefined, but we basically don't want to deal with those. Okay. So a different way to look at it is according to year. So here we have a graph that shows us for each year in the range 1892 to 2013, how many stations produced an actual read in those years. And what we see is that there's a clear trend that before 1940, there were very, very few. And after 1960, there were significantly more. even though, sadly, if you look at the trend since 1960, there's more and more NANs. Okay, um, so what we chose to do here is basically concentrate on the years 1960 and on. And once we do that, we concentrate only on those years, then we have a better density. We have that only 66% of the elements are NaN. So even that might be discouraging, but it seems to be enough to draw some meaningful conclusions. After we remove those years, the years since 1960, we have a distribution of undefined which is a little bit better. We still have a majority that have very high fraction of undefined, but we overall have a more flat graph. Okay, so now we want to estimate the effect of year versus the effect of station. So we're going to do it by taking the mean over the stations, over the columns. So that would give us for each year, it would give us, for each station, it would give us an average. And if we average over the column, then it would give us a mean by year. Okay, so so what we can do now is basically see, okay, how much is the year, each individual year, different from the prediction according to the average over the years, or the prediction over the columns. So what we see here is basically that if we look at the total error before we subtract the mean, then we see that the error is 758. So that's the error relative to the mean of everything. And then if we look at subtracting the mean by station, it reduces it to 705, so a reduction of 52. And then if we remove the mean by year, then it reduces it by to 539, which is a reduction by 219. So basically these numbers here, the 52 versus the 219, give us a quantitative measure of how much more important is the year versus the station. Okay, so the year, if you take the mean by year, you reduce the RMS by 219, which is about 4 times what you get if you remove by station. So that's one important conclusion we can draw. So what we found is the effect of time is about 4 times as large as the effect of location in terms of the time that the snow season occurs. Is it early or is it late? So what we can do even beyond that is that we can do an iterative reduction. So once we subtracted the mean according to the years, let's say, then we still have a residual which we can try to explain using the stations. And once we subtract that, we can go back to the years and correct that. And eventually, we want to subtract a vector for the years and a vector for the columns such that no change will be evident. So basically, after subtracting it, every row and every column would have a mean of 0. Okay, so this is what we're doing in this program here. And what you see is that this process converges very quickly. So you start with an error of 758. You remove the year, so you get 539. Then you remove the station. It improves to 494. And then you get slight improvements as you go. But you see that after about 2 iterations, there is essentially no reduction. So now you have 2 vectors, the row vector and the column vector, that are that are basically stable. So by subtracting those, you get columns and rows that whose mean is 0. So one thing that is interesting to do with this model, we can think about it as a model of the influence of the year, a model of the influence of the station. And we can look, is there a trend in terms of the years? We know the years are important, but are they important just randomly going up and down, or is there a general trend? So here is a little plot of basically the vector. And what we have here as a function of the year is the value of the average that is stable. And what you see is that there is a clear trend upwards. Okay? So it seems quite clear, according to this, that the trend is that snow is getting to be earlier and earlier. Okay, but notice that the range here is pretty small, right? So it's minus 0.15 to 0.2. Now, if I look at the box plot for the same years, just looking without subtracting anything, what I see is the main thing that I want to point out is that the range of values is between minus 4,000 and 4,000. So the whole range we're talking about here in terms of trend is a tiny, tiny, tiny trend around here. And it is next to impossible to really deduce from this whether there is a trend up or a trend down, because what we did was a very careful model of the average over the years and the average over the stations. And after we did that by modeling, if you will, we found that there is a residual trend on the years. Okay, so this trend is completely in the noise if you look at the actual distribution. So to summarize, the problem of missing data is prevalent. We talked about it before, and we'll talk about it again. It basically can never be assumed to go away, because unless you have some kind of sensors that are always on for the whole duration and all of the sensors work correctly, when you're using large-scale data, there's going to be a lot of missing data. The RMS we used to quantify the effect of different factors. Here, the factors were time versus location. And the snow season in New York has been getting earlier and earlier since 1960. That seems to be a pretty clear trend, even though it's a weak trend. It's not a trend that you can say has a huge effect. So with this, we finish our analysis of the New York weather, and we'll continue next time with some view of how to improve the analysis for precipitation and some other measurements that are very noisy. See you then.